Hello everybody, this is our video solution to problem 4 from the Spring 2021 Math 302 final exam. This is another problem about ideals. Here though we're going to be talking about the GCD of two ideals and the least common multiple of two ideals, showing that we can actually generalize some results from just basic integer divisibility, right? Formulas for the GCD and the least common multiple to the world of ideals, which is pretty cool. So let's look at what we have. We have a commutative ring with identity, and this is actually all going to come into play. That's actually going to be a key assumption here. We're going to use that. We have two ideals, A and B, of this ring R. And we have assumption that the GCD of the two ideals is equal to R. So we better explain what that means. So the GCD of the ideals A and B is defined to be the sum of the ideals. Okay, so the sum of the ideals, that just means you look at all things of the form little a plus little b, where little a is in ideal A and little b is in the ideal B. So you get all those pairs, and that's what we define the GCD of two ideals to be, and we're assuming here that this is equal to the whole ring. And the key thing here is, right, if you know that your ideal is equal to the ring, and we have a commutative ring with identity, then your ideal must contain, of course, the identity, which means we can write the identity of R, right? So the identity of R1, we can write it as something in A plus something in B. So 1 is going to equal some maybe U plus V, where U is an element of ideal A and V is an element of the ideal B. All right, so that's just what the assumption means. And so then, well, we actually have a problem. We want to prove that the least common multiple of the ideals A and B is equal to the product of the ideals A and B. So once again, we better explain what those things mean. So the least common multiple of the ideals A and B, this is the intersection. Okay, this is just the definition. It's the intersection of these two ideals. So every element of the ring that's in both of the ideals A and B. All right, well, what does this product of A and B mean? So the product of two ideals, well, remember, if we look at the sum of two ideals, we might be tempted to say, okay, it's all products of elements from A and B. And that's great, except for this teeny little problem that doesn't give you an ideal. You have to take sums of all such products. And that's because ideals need to be closed under addition. Right? If you just take products, you're not guaranteed that you're actually going to be closed under addition. So we're going to look at all products, or some, I call them sum products of A, B. So here all these A, I are in A, and all these B, I's are in B. And this is for all I. This is a sum over I. Okay. So that's what the product of two ideals looks like. And our claim in this problem is with the assumption that the GCD of A and B is equal to the entire ring R, that the least common multiple is actually equal to this product. So, well, we have to show reverse containments here. All right? So let's see. Let's step one. We'll show that the intersection is contained in the product. All right? So let's assume I have some element in the intersection. So we'll let X be an element of the intersection of A and B, so we know X is in A and X is in B. Now, we have an expression for 1, which means I can take X and multiply it by 1. Okay, and I don't change anything. But then I can replace 1 by U plus V. And so this will, by distributivity, will equal XU plus XV. And now I'm going to make a small change to the ordering, and you'll see in a minute why I want to do that. I'm going to write this as UX plus XV. All right, and because I'm in a commutative ring, that's okay. I can do that. Now, what do we know about U? U is an element of A, right? That was our assumption. And x, well, it's in the intersection of A and B, and so it's an element of B. On the other hand, x is in the intersection, so it's also an element of A. And V, that by assumption is an element of B. And so here I have a sum product, okay, of elements from A and B. It's, look, something in A times something in B plus something in A times something in B. And that's precisely what it means to be an element of AB. Therefore, I've shown every element of the intersection is an element of the product. So we conclude A intersect B is a subset of the ideal AB. All right, well, now we just need to show the other direction. And this is actually the easier direction. All right, so now we're going to show that AB is a subset of A intersect B. All right. Well, this actually just follows because of the absorption properties of ideals. So to show that, by the way, that the product AB is contained in the intersection, in principle, we've shown that all of these sums, right, are in there. But we know that if you can show that all such products are in there, then you're also going to get that all such sums of products are in there because A intersect B is an ideal. All right, so let's start with that. So since A intersect B is an ideal, it is closed under addition. So it suffices to show that all products of the form AB, where A is in ideal A and B is in ideal B, so all such products are in the intersection. Right? If I can show all such products are in the intersection, then all their sums have to be in there because A intersect B is closed under addition. All right, but if A is in A and B is in B, okay, so that's what's going to build one of these products. Then since A and B, the ideals, right, absorb multiplication, right? That's the other big property of being an ideal. You closed under addition and you absorb multiplication. What do we know? We know that if I take A times B, well, A is an element of A. And when I multiply by B or anything else, I stay in A because the ideal absorbs multiplication. So this product is in A. On the other hand, B is in ideal B. And B absorbs multiplication. So when I multiply it by A or anything else, it stays in B. So this element is in both A and B. So all the products are in the intersection. And so we conclude that the product AB is contained in the intersection. But now we have both containments, right? Thus, AB equals A intersect B. And remember, A intersect B is our definition of the least common multiple of A and B. All right, so that was the first part of the problem. What's the second part? Use the previous part to conclude that if two integers, x and y, are relatively prime, all right, so their GCD is equal to 1, then the least common multiple of x and y is equal to x times y. All right, so this is actually going to be a fairly immediate conclusion because, so first, if the GCD of x and y is 1, then what does that tell us about the ideals generated by x and y? Well, we know that 1 is going to be in the ideal generated by x plus the ideal generated by y. Why? Well, Bézout's lemma, right? Here, maybe we should write all this down. So this will be part, do we call it B? Okay, we'll call this part B here. So we have that GCD, the GCD of x and y is equal to 1. So by Bézout's lemma, we can write x and y, or rather, we can write 1 as a z linear combination of x and y. So there exist integers s and t such that 1 is equal to xs plus yt. But this is an element, right? xs is a multiple of x. So this is an element of x plus a multiple of y. So it's in the ideal generated by x plus the ideal generated by y. And of course, the sum of these two ideals, this is the GCD of the ideal generated by x and the ideal generated by y. But once we get 1 in an ideal, then we know that the ideal equals the whole ring. So thus, the GCD of the ideal generated by x and the ideal generated by y equals the ring of integers. Okay, well, we go back up to our statement. That was the big assumption, right? We have two ideals. In this case, we're looking at the ideal generated by x and the ideal generated by y. And the GCD of those two ideals is equal to our ring, which in this case is the ring of integers. Z, of course, is a commutative ring with an identity. And so we conclude that the least common multiple of these two ideals is equal to their product. Okay, so by part A, the least common multiple of the ideal generated by x and the ideal generated by y is equal to the product of the ideal generated by x and the ideal generated by y. And of course, in class, we even showed that in this situation, this is equal to the ideal generated by x times y. All right, now what was our goal? Well, our goal is to show that the least common multiple of x and y is equal to x times y. And well, we're so close, except our statement at the end here is at the level of ideals rather than elements. So we got to turn this into a statement about elements, right? So our claim is that the least common multiple of x and y, right, almost the same thing, is equal to x times y. Okay, so make a little room. So we observe that the least common multiple of x and y, well, it's a multiple of x and y. So since it's a multiple of x, it's in the ideal generated by x. But it's also a multiple of y. So it's in the ideal generated by y. But the intersection of these two ideals is precisely the definition of the least common multiple of these two ideals, which we know is equal to the ideal generated by xy. And so we conclude that the least common multiple of x and y is a multiple of x times y. So we conclude the least common multiple of xy is some multiple of xy. So this is equal to m times xy for some integer m. Okay, but we also know that it's the least common multiple. And at this point, I see there's actually a small typo in the problem, really an omission. So we definitely want to assume here, as one normally would, that x and y are positive integers. So that way everything here has to be positive, right? So we know that x times y is a positive integer. The least common multiple, right, that's always defined to be positive. And so if we want the least common multiple to be the smallest multiple, right? It's the least of the multiples, right? Well, then what can m be? Well, the smallest m could possibly be is 1. And in that case, you just get x times y, which is a multiple of x and y, right? It's a common multiple of both x and y. right? So since the least common multiple of x and y is the smallest multiple of x and y, we must have m equals 1. Right? It can't be any bigger, because then it wouldn't be the smallest one, right? Because we know xy is a multiple of x and y. All right. But if m is equal to 1, this implies the least common multiple of x and y equals x times y. And that completes the proof.